Okay, let's take a look at this question. We have fluorine gas serves an important role in the nuclear cycle system, and it changed the uranium ore into UF6 gas, which is needed to separate the uranium isotopes. And then the fluorine gas flow can be produced using electrolytic process of HF in a molten KF. At 130 degrees Celsius. And then here we have the standard electrode of hydrogen, which is 0 volt. And then here we also have the reduction potential for the K plus becoming K. Question A, we have to write down the reaction in the anode and the cathode for the above electrolytic process of HF. Now here the HF or the process doesn't involve water, so in this case we don't need to compare the electrolytic probabilities of water. So let's say in HF, here we are going to have H plus, this is actually H plus, and then F minus. So we have H plus and F minus. Let's say the H plus becoming H2. Wait, why do we have K plus? Okay, so the probability is that the H plus will then becoming H2, so from +1 to 0. So we have like a decrease in oxidation number. And then another possibility is that F minus becoming F2. So we have like from -1 to 0, and that is like oxidation. But then here we have also a molten KF, so there is K plus here. So for that, K plus becoming K. So in that case, we are thinking about the possibility of reduction. So it's at cathode. So at cathode, that should be reduction. So we are going to put two possibilities here. We have the possibility. So the first one here is we have H plus, and then this will result in H2. So this is gas, and this is aqueous. But then here we have to balance the charge, so I'm going to add electron here, so we balance the charge. And then the second possibility is that we have K plus, which is also aqueous, and then we have like electron here, and then it will result in calcium metal. So this is solid. So what should we compare? So we should look at the reduction potential. So the reduction potential here from H plus becoming hydrogen is 0. That's the standard hydrogen potential. And then the reduction potential of K plus becoming K, here we have like minus 2.94 volt. What does it mean? So if we compare the reduction potential, the one that has positive value, so the more positive, the better. It means that it is easier to be reduced. And we are talking about the reduction process at cathode. So in that case, this one is more possible. So this is the reaction that is going to happen at cathode. While at anode, because HF and KF both result in F minus, so we just write down the F minus reaction. So in this case, we have F minus, and then we will have F2. So we need two to put here too, and then we have like 2 electrons here, so that this is gas. So we balance the equation. And then so this is like the reaction that is happening So the answer is this one, it's cathode, and this one is anode. Here for the K plus becoming K, it's hard to reduce. Okay. Well, this one reduction is more possible. Now, the question B, calculate the volume of the fluorine gas in liter at 130 degrees Celsius and 1 atmosphere, which is produced by the above electrolytic process by applying an electric current of 10 ampere for 2 hours. So in that case, we are going to take a look at the reaction at anode, because that is what relates to the fluorine gas. So here we have 2F minus becoming F2, and we have 2 electron over here. Now we have the information of current, electric current. So this is the value of the electric current, and this is the value of the time, but this should be in seconds. So 2 times 60, then we got the minutes, and then time 60, another 60, then we got the seconds here. So here we have 7,200 seconds. So the next one here we have Q, which is the charge, the coulomb. This is the formula, and this would be the same as the NF, and which is N here is actually the real mole of the electron. So in that case, what we are going to calculate is the number, the amount of the electron, which is electric current times time, and then divided by the F. So I'm going to have 10 ampere, and then the time should be in second, and then here we have, which is coulomb per mole. After we know the volume of the electron, we can calculate the after knowing mole of the electron, then we can calculate the mole of the fluorine gas. So the mole of the fluorine gas is half of the mole of the electron. So in that case, this is the mole of the F2 gas. And then we are going to convert this into a liter. So we're going to use the ideal gas law. So this one is volume. So the mole of the fluorine here is this value. And then the R that we are going to use is this one. So this is liter atmosphere. And then the pressure should be in atmosphere. So this is the volume. So this is the volume of the fluorine gas.